Did you have a chance to do this, or should we just go to the lesson here? Do you want to get one knocked off the homework? Do you need to review this, or no, just move on? Review it? Okay, cool. You want to give it a go on your own and see how you would do, or now you really don't know what to do, let's all do it together. Let's try it. Try it on your own. That's the spirit, Brandon. Okay. Then you can look at your work, and I can tell you if you would have had full credit based on what your work looks like. The work is important here. Oh. That's very good. All right. I will make clear what I would want to see besides the answer, what I would want to see. How did you start? What did you do to begin with? I hope you just kind of got a general clue. What is the point of the problem? We're trying to estimate the cubit of 68. How? Based on some starting point, I heard? Some starting point plus some change. So I would take, if you just said this is like cubit of 68 is like 4 is like 4 plus some change or something like that. That's cool. I will tell you this, if you went straight to this, 4 plus dy, to me that does not communicate the big idea. So the very first thing I would look at is, I don't care if you put the 4 later, if you just looked at the change the whole time and the 4 comes later, but the very first point I would have is you know delta y is approximated by d. Do I have somewhere in your work delta y approximately dy? After that then, I would look to see, do you know how to find dy? Okay, how do you find dy? F prime or y, if you use y prime, I said off to the side, let y equal f of x. So you could call it f prime. If you said y prime, that's fine. But it needs to be some kind of derivative at the initial times dx. That's my second point. You know how to find the differential dy, and it's the derivative times the differential of the independent variable. Depending on the problem, that could be v and r, or f and dx. So it could be a lot of things. It depends on the problem. You with me? Are you showing good quality work so far? I hope so. So what is the derivative of cubit of x? 1/3 x to the negative 2/3. And at what point do I evaluate it? 68 or 64? 64. Dx, is it negative 4 or positive 4? Positive 4. Now, I beg you, please don't get embroiled in some kind of silly memorization. Is it n minus start or start minus n? Just ask yourself, what makes sense? Is cubit of 68 going to be more than cubit of 64 or less? More. So it should be positive 4, right? Are you with me? All right, what is the cubit of 64? Somebody? Or what'd you get for an answer? 4 and 112? That sounds familiar. Okay, cool. All righty then. That's the work I expect to see. Make sure you have good quality work. All right, this lesson, I'm going to have to take a little longer on this lesson than I normally would. Now, here's stressed out last year. She was stressed for days, and she came to me and said, "Can I go parametric control?" So you guys have not ever got parametric control, whereas normally when I get sick, when they have. So I'm going to treat this from a very basic level, beginning. You've never seen it before. Do I have that right? Have you ever? If I say parametric equations, does that mean anything to you? No. Okay, good. And I'll teach you. Here we go. Parametric equations are awesome. Tomorrow we'll probably do this. We're going to, being a math nerd and be in the math hall, and I'm not the only math teacher that does this, I can tell you this. When you walk down the hall here, you might have noticed that there are diamonds. And like a lot of math people, and actually like a lot of 8th graders, you sometimes, when you're all by yourself and nobody's looking, you walk that way down the hall. Now, that's pretty cool. And the beauty of parametric equations is that I can model that. I could make a cartoon of a person doing like that by writing equations for the movement. Now, the equation of this in x and y is not too hard. You could easily do x's sine y, and that makes that graph. It shows the position, but what it doesn't show is when it is, where it is. And that's really how movement works. If I said, hey, where are you? Here's the path. Here I go, I'm moving. If I said, hey, where are you at a certain point? It would be stupid to say, well, once you give me the x, then I'll tell you the y. Where you are horizontally shouldn't depend on where you are vertically, vice versa. They should both depend on when. And so parametric equations do the job of saying not where are you, but where are you when a certain point in time happens, or when you are where you are. Now that idea then is, instead of relating x and y directly, your horizontal position in space and your vertical position in space, you don't relate them together through one equation. Instead, you relate them both to time in two equations. That's parametric equations. Two, and I'll say or more, because in Calc 3 you will do 3 space or 3 parametric equations. Equations for horizontal and vertical position depending on time. Now, a parameter is a condition. So the parameter, or the parametric equations, that's time. Time is a parameter or condition. Often you're going to hear that in college and say, what are the parameters on this study? What are the parameters on this problem? Okay? They're conditions placed on the problem, or restrictions. All right, now, I think I have these in the wrong order based on the fact that this is totally new. This is a lot. So instead, let's go to an easier one, all right? Let's go to the usual. Now, usually, like I said, parametric equations are used to show movement. And so you will often be graphing the movement. That's the idea of the first problem. Sketch the curve generated by the parametric equations you're given. Let's start with a table of 3 columns. At time, you're going to find x and y. And let's just go through 4 settings. That should be enough. Depends on the problem, but in this case, I think it's best to just find all the x's. Once you're in x equation mode, just keep in x equation mode, and then switch gears and do the y equation. So, when time is 0, what is x? So your horizontal position on the graph. 8. When time is 1, what is your horizontal position on the graph? 6. And you probably see the pattern. 4 to 0. Where's 0 coming from? Okay, you're moving horizontally in a linear way, but we'll talk about that in a second. Y, negative 3 plus t squared. At time 0, your position is negative 3. At time 1, your vertical position is negative 2. When time equals 2, y is negative 3 plus 4, or 1. When time is 3, y is negative 3 plus 9, or 6. And when time is 4, y is negative 3 plus 16, or 13. Would you draw me a first and second graph with most of the room in the vertical positive direction. Go to 2, 4, 6, 8 in X and -3 to 13 and 1. Right? All right, now we're going to graph, and it's got a little more to just graphing than the average graph. It's got more. Now, looking at the table, then, time has done its job. This is horizontal vertical position. So what I'm graphing here is X against Y. All right. So the first point is 8, -3, that's down here. 6, -2. 2, +1. Why did I go 2, 4, 6, 8? Oh, stupid. Sorry. Sorry, I started looking at the T's. This always happens to me. Sorry. 4, 1. You with me? Sorry, I started looking at time column. 2, 6, and 0, 13. Oui. Now it is a smooth curve, so feel free to go whoopity-doo, but do not extend it yet. Now, time is only 0 and up. So this isn't just forever in both directions. It is only forever in one direction. Now, when you do parametric, you should always show the initial condition or show the initial point. Show initial. Say, mark it with, this is initial point t equals 0. You follow? Now this does continue to go. As time goes, it does go forever. So do put an arrow there, because it goes forever in that direction. But here's a little more. Parametric equations are supposed to show direction of movement. And so you will also include an interior arrow. Include interior arrow to show direction. Now you might on this graph think, is that really necessary? I mean, I show the starting point, and the only way the rest of the curve is going to be made if I go that way, right? I agree. But here's the deal. In a second here, you're going to graph a thing that goes like this. Well, if I say time equals 0 is here, which way do you go? I guess you'd have to say, I'm going this way. It goes this way. So you are, the more complicated it is, the more arrows you're going to put on. But yeah, that direction of movement has to be there. It has to be there. All right? You can put as many arrows as you like on there within reason. Don't get 20 with me. I want you to get like 80 arrows. That's stupid. But that's the idea. Are you with me so far? Are you with me so far? Cool. Let's try a harder one then. We'll go back to the first one, which you can see is considerably harder. Let's go with time x and y and 0, 1, 2, 3, 4. Actually, I might give myself a little more room because there's going to be a little more thinking involved for these calculations. I might need to do some more. I don't know. Okay, so what about when 0 goes in? X is 0 plus cosine of 0. What's 0 plus cosine 0? 1. Okay? What about when we put 1 into the x? 1 plus cosine pi over 2. That's 1 plus 0, or that's 1, yeah? What about 2? What do you get? What is it? 1, yeah. 2 plus 1 is, or 2 minus 1 rather, excuse me. 2 minus 1 is 1. So if you're thinking, yeah, it's not even moving, that's not true. But it does look like it. 3. 3 plus cosine 3 pi over 2 is 3 plus 0, or 3. Follow me? 4. 4 plus cosine of 2 pi is 5. All right, cool. We'll graph that in a second. First we need the y's though. When you put y of 1 or 0 in, What's sine of 0 minus 0? 0. What's sine of pi over 2 minus 1? 0. What's sine of pi minus 2? Negative 2. What's sine of 3 pi over 2 minus 3? Negative 4. And what's sine of 4 pi over 2, or 2 pi minus 4? Negative 4. All right. Now then, let's graph. In terms of space, it looks like I only need positive x's and mostly, or almost all negative y's. Are we cool? So 1, 2, 3, 4, 5 and x should do. 1, 2, 3, negative 4 and y should do. The initial point is 1, 0. Mark it. Time equals 0. There's my starting point. Next point is still 1, 0. Did it not move? Well, I guess the question on that would be, is there a time between 0 and 1? Yeah, there's a time between 0 and 1. Let's go with 1/2. If I did a half, I get a half plus cosine of pi over 4. So that's a half plus root 2 over 2. So does it move off that? It does, okay. We'll look back at that in a second, but for now, let's just say it's there. I know it's moved, and it's back to that spot, but we'll talk about that in a second. The next point is 1, negative 2. And the next point after that is, oops, I just graphed 0, negative 2. 1, negative 2. Or I graphed 2, negative 2. 1, negative 2, and 3, negative 4. And 4, negative 4. And it seems like it's going this way, yeah? Are we cool? But the graph is a little cooler than that, quite frankly. So, pick up the cup. And go to the graph screen, and you need to change graphing mode. You no longer are going to graph function mode, you're going to graph parametric mode. So go to menu, graph entry, which is 3, and choose parametric. Now it'll switch the template from function to parametric equation mode. And type in the equations. The first one I can't remember was t. You have to use t here, not x now. T plus cosine, was that right? T plus cosine of pi t divided by 2, and y is sine, I think. T divided by 2 minus t, is that correct? Minus t, and hit enter. Boom. Okay, so you're not seeing, my graph is all congested. So this is what I'm going to do. First of all, I'm going to grab those guys and move them out of the way. And second, let's zoom in on this. So the other, I have, like you probably have your favorite zooms. I definitely have my favorite zoom. My favorite zoom is Zoom Box. If you go Zoom Box, then you can just say, hey, I want to see this piece a little better. And that's a little cooler. You can see then that it's definitely not like we thought it looked. There's a little more funny business going on. And so if we are to graph this or improve our graph a little, we would say, why generally does it do this? Think about the equations. As time goes on, yeah, the cosine will give me a little back and forth, but isn't cosine fairly limited in what it can contribute? What's the limitations on cosine? At most it's 1, and at least it's negative 1. So really this is behaving in a x gets bigger kind of fashion. Y is a negative t plus a little trig action. So y is going to constantly decrease, and yeah, the sine will give it a little back and forth action. But it makes sense that generally it's going this way, yeah? as you went further out, that the effect of the trig, would it be more or less? Think of the magnitude of the numbers. When you get to 1,000, x is going to be 1,000, and then the trig is going to throw in some little 0.3. Is that going to contribute much? Now, if you want to see more, go back to your graph and say, I don't want you to stop at 6 seconds. I want you to go to 12 seconds. You can see it went through 3, 2 pi. If you let it go for a little more, then it'll go a little further. Now my zoom is a little off, so I'm going to zoom out a little bit. And you can see that you get a little more action there. Yeah? You follow me? No? Did you say no?
How did you change the two?
How did I change the what? Oh, sorry. In the tab, in the equations, go to the time at the bottom, the domain of time, and just scroll down there and something bigger than 2 pi. Change it. I changed it to 12.28 isn't anything, but you get the idea. You with me? All right. What do you reckon t-step is? Think about your table, okay? We calculated every second, and we got a pretty choppy graph, yeah? It looks more like this, this, this. Now we could get a better graph if instead of calculating position every 1 second, we calculated every 1/10 of a second or 1,000th of a second. That's what t-step is. That's saying calculate position every 0.13 of a second, okay? If you're getting a really choppy graph, you might say, is my t-step small enough? Now, if you get crazy and say, all right, t-step, 0.000001, what's going to happen? You're asking your calculator to calculate position every billionth of a second. That's a lot of positions you're asking to calculate, so your calculator is going to go, give me a minute, give me a minute, give me a minute, and it's going to be stuck in over. Okay, so don't get crazy with the t-step. All right. Understood so far? Everything going okay? All right, let's go on a little more. There's no way I'm going to get through all these notes, but we'll continue tomorrow. This one. Okay, now, so, Brandon, if I said, hey, what does that equation, that parametric equation graph look like? Go, quick. Would you not? Too slow. You're slow. Sorry, not good. All right. Now, my point is this. While you don't know a lot about parametric equations, you know a crapload about x and y equations. You can graph the heck out of x and y, yeah? Now, because of that, you sometimes need to say, you know what, if I really want a good picture of this, I'm going to dump the t and relate y and x directly so I can just see what the x and y positions are, and I'll sweat the time later. Now, when you dump the t, you're eliminating the parameter. Sometimes you eliminate the parameter to get a better view of the graph. If you eliminate the parameter, you're trying to relate x and y directly. You're going to do this 2 totally different ways. If it's algebraic, use substitution. If it's trig, use identities. I will explain what that means in a minute, but for now, let's do the first one. That's an algebraic set of parametric equations, so we're going to use substitution. If I want to relate x directly to y, then I can solve one of them for y, or t, excuse me, and substitute it in. Which one's cleaner to sub for t? The x is cleaner to sub for t. Y is solving for t better in the x coordinate. Right? Because y you're going to get, what are you going to get if you solve for? Plus or minus. You don't want that. All right, so solve the one that's clean. So if we solve for x, or the x equation for t, isn't t x minus 3 divided by 2? If that goes in to the y equation, then y is x minus 3 over 2 all squared, or if you like, 1/4 x minus 3 squared. Now, Brandon, can you tell me what that graph is? I was hoping you'd say yes. Okay. All right, that is graph we know. We know it's a parabola, and we can graph that. But the graph is complicated. It's just not just a normal mindless parabola. There's more. So now graphing this. Actually, let's not even graph this yet. Not ready for graphing yet. When you eliminate the parameter, because time starts at 0, we don't typically do negative times. They said time is only positive. Not every x, and maybe y, is made. I won't get the whole parabola because the only times I was allowed to put in were non-negatives. What kind of x's will I get out if I'm only putting in non-negatives? From where on up? What's the least x I can get? 3. The minimum x is 3 and up. All right. I'll come back to that in a second. Let's do graph with equation here. Wouldn't you agree that this is a parabola shifted right 3 and it's y? So I'm going to go real light like that, yeah? Okay, now, because time is greater than or equal to 0, that implies x is greater than or equal to 3. So when you write your answer, it should have the xy equation, y equals 1/4 x minus 3 squared, and a domain restriction. X, hey person reading this, yeah, it's the parabola graph, but it's only for x is greater than or equal to 3. And your answer to the eliminating the parameter question should actually have both of those things, not just the equation. You with me? Now the graph, because x is only greater than or equal to 3, we're only getting this part of the graph, not that part. And now we have a parametric graph. We still need to, we're graphing the original movement. So we're still graphing parametric. The parabola helps us know what the path looks like, but we're still trying to show movement. So we need to show two things. What do we need to show? T equals 0 is here, and the direction of movement. What's the direction of movement? You might think again, well, there's only one way to go. But I remind you, there are going to be cases where it's not so clear, this is the way you go. So, will you write yourself a quick note? Finding direction arrow. Two ways. One way, call it method 1, put in time equals 0 and time equals 1, and say, where did it start and where did it go? Now, if I do that, I know the initial point is that starting point, and when time equals 1, I get 5, 1. So doesn't it, as time passes, didn't I have to go that way to get from that point to that point? You down? Or, method 2, my preferred method, just because, not because it's easier, it's actually harder, but it's more fun, is calculus. What is dy dt? Dy dt is 2t. Okay, I took the derivative of t squared there. We need to review the power rule. Very good. The derivative of t squared is 2t. Are we good? Okay. All right then. Now, what that does for me is this. If time is always positive, then dy dt is always positive, and therefore y must always be increasing. If time is positive, then dy dt is positive. so y is increasing. It's got to go up. What if you took the derivative on x? What's the x, do you see? 2, yes, 2, do you agree? And therefore x is, I'm so sad that I had to check your work on that. Is 2, and therefore x is increasing. All right, and so that also makes sense. It's moving right and up. It's moving right and up. All right. Let's go with trig now. Different animal. First, I still, no matter how much I always say, you've got, yes, sorry.
You don't have to show range at all.
So good question. Range I'll take only when it's necessary. I'll give you an example when you do have to show range. In this case, actually, let's do it just to be safe. There are always questions, do I have to show the range or not? The safest way is always to show range. So what is what? Greater than or equal to 0. Good call. Thank you. I probably should have done that. X greater than or equal to 3 kind of forces y to be greater than or equal to 0, but it's fine to put it also. All right. Now, no matter how much I say on trig, use identities, don't use substitution. There's always some knucklehead the first day who says, screw, I don't remember how I'm supposed to do this, so here I go. T is x minus 3 over 2 and the inverse sign of that, yeah? Do you agree? And then they put it in there and they say, okay, the equation is 2 plus cosine of inverse sine of x minus 3 over 2 and all that squared. Okay, now if you do that, I'm going to give you your test back and I'll say, all right, I won't take off 4 yet. If you can graph that, graph it, go. Yeah, exactly. I don't know. Yeah, there is no way. Nobody knows what that looks like. It's a crazy mess. You wouldn't graph that. That's insane. Okay, not to mention domain and range of arc sine. It's terrible. Terrible. No. Okay, so instead, you'll use identities. Use the fact that if somehow you could get sine squared of t and cosine squared of t, then you could replace all that with 1. Okay? Now, all you have to do is get sine squared. Get sine squared. It's not hard. How do you get sine squared then?
1 minus cosine squared.
No. Good try. Okay? How do you get sine squared out of this equation?
Oh.
You'll need to square it. Do you want to square it first while it's a binomial, or would you rather move stuff first? Good call. Okay. So subtract 3, divide by 2, then square. So sine squared is x minus 3 over 2 all squared. You see where I'm coming from? Okay. Now get cosine squared. Do this right below. It tends to organize well if you do this right below. Cosine squared is even easier. It is just 1 minus 2. Now, fundamental truth of math, which is how we use elimination, is if you have 2 equations are true, you can add them to get a third equation and it'll be equally true. So when I add the left side, what is sine squared plus cosine squared? 1. The t's are gone. And now I just have x minus 3 over 2 squared plus y minus 2. Now that's still pretty gross, so let's clean it up a little. Clean it up so graphing is obvious. Sometimes you'll get a circle, and I would try and go for circle equations. Sometimes you'll get an ellipse, so I'd get an ellipse equation. Put it in some kind of standard ellipse form. What kind of graph is this? It's a parabola. So let's go standard parabola form solving for y. Y is negative x, let's just go negative 1/4, x minus 3 squared and plus 3. Yes? Okay, I'll finish tomorrow. You should be able to do a good chunk of the homework. Have a lovely day. 106 is due Friday, not tomorrow. Oh, shucks. What about 105? Give me the hands on 21. All right.
Let me go over a couple of them.
Let's just turn it in, shall we?
105.
105 too. Gotta be fair and good period.
I didn't ask. That was on me.
Fourth, fifth period, they shouldn't be screwed over, right? As long as you get it out of the door, you're good. Have a lovely day. It's a great day for me. Uh-oh.